Good day, dear colleagues and committee members. My name is Yuri Skop, and I'm presenting our collaborative study that leverages 3D CFD modeling to enhance the infrastructure safety of modern green energy fueling facilities. The research objective is to numerically simulate a catastrophic explosion of a high-pressure hydrogen cylinder at a fuel station and compare the efficiency of 10 protective engineering configurations. The object covers the physical gas dynamic processes of hydrogen cloud expansion and its structural interactions. The subject includes the 3D overpressure and impulse fields along with peak barrier loads. Methodologically, we utilized a 3D finite volume CFD approach based on the Euler equations, solved via an explicit first-order Godunov scheme in our specialized software system FIRE. The relevance of this study stems from the rapid growth of hydrogen infrastructure. Equipment failure can lead to immediate hazardous gas release. Due to hydrogen's high combustion velocity and wide flammability limits, explosive gas mixtures frequently generate devastating blast waves. This causes rapid overpressure damage, shrapnel hazards, and potential domino effect collapses, making robust engineering barriers vital to isolating these industrial risks. We formulated a 3D mathematical problem statement using a hydrogen cloud model. The domain captures the time-dependent three-dimensional flow of a two-component gas mixture using partial differential equations. Equations describe the conservation of mass, momentum, total energy, and the mixture components, enabling reliable tracking of shock fronts. Figure 1 and 2 show the barrier geometries and control points, P0 in front of the wall and P1 and P2 behind it. Looking at the overpressure histories, Figure 3 reveals a major challenge at point P0, where solid barriers cases 1 to 4 cause massive pressure accumulation due to dynamic wave reflections, increasing peak overpressure up to 2.5 times. Conversely, Figure 4 shows that these same cases exhibit the most pronounced overpressure reduction directly behind the wall at point P1 and P2. Figure 2 provides a visual representation of the transient pressure distribution for case 1 at different time steps, demonstrating how the shock front impacts the solid wall, diffracts over its edges, and forms a shielded shadow zone. Figure 3 shows that extreme maximum loads concentrate at the center of the wall surface. To mitigate this localized loading while maintaining downstream protection, we designed alternative configurations, such as Case 2, which introduces a bypass channel under the wall. We expanded our investigation to advanced geometries. Figure 1 visualizes how the bypass channel in Case 2 successfully shifts overpressure profiles. Figure 2 displays Case 4, featuring a protective T-shaped top profile that reflects the upward diffracted wave. On the other hand, Figure 3 shows Case 5, which utilizes a deepened explosion zone pit, and Figure 4 shows Case 6, which relies on unloading cavities. These configurations modify the shock wave topology to reduce structural stress on the barrier. Another innovative approach involved replacing solid walls with porous shock dampening column packages. We tested layouts under template 1, case 7, and a denser layout under template 2, case 8. As seen in the transient profile on figure 2 and 5, these column configurations force the monolithic blast front to fragment into smaller wavelets, promoting intense turbulent dissipation and destructive wave interference to effectively lower the cumulative blast energy. To synthesize our findings, peak metrics for all 11 scenarios were consolidated into tables 1 and 2. The data highlights a clear engineering trade-off. Walls protecting downstream personnel often suffer the highest destructive reflection loads at P0. However, case 9 emerges as the most efficient compromise. It achieves maximum mitigation behind the wall while keeping the structural reflection load at P0 below the unprotected baseline level. In conclusion, we thoroughly investigated the 3D physical gas dynamics of a high-pressure hydrogen cylinder explosion. The explicit Godunov-based 3D CFD model proved highly effective for tracking shock front parameters. Our comparative analysis identified that while solid T-shaped walls perform well, a package of two adjacent perforated walls combined with a deepened explosion pit provides the most balanced, robust safety level, significantly improving operational protection at fueling stations. Thank you very much for your time and attention. I am now open to any questions or comments you may have regarding our study.